Homework 3A. The evolution of life requires the organization of a very large number of molecules into biological cells. Does the formation of living organisms violate the second law of thermodynamics? In this question, it says the organization of a very large number of molecules into biological cells. This implies the entropy decrease, because we know entropy is a measure of disorder, and so when the molecules becomes more ordered, the entropy decrease. And therefore the question is, does this violate the second law of thermodynamics? We must remember that the second law of thermodynamics states only the total entropy of both system and the surrounding must increase in a naturally occurring process. It does not state that entropy must increase in a portion of the universe that interact with the surrounding. In this case, the cells grow by using chemical energy from the surroundings, and in the process, the entropy increase in the median outweigh the decrease in entropy of the system, and therefore the second law is not violated. Question 2. Under what conditions is delta S less than 0 for a spontaneous process? Now this question is related to the last question. The second law says for a spontaneous process, the total entropy must increase. So the entropy change for the system, entropy change for the surrounding adds together must greater than 0. So sometimes the entropy of the system can be less than 0, negative, if the surrounding entropy increase more than the entropy decrease in the system. For example, if the system entropy is -5, the surrounding entropy can be 9, so that when they add together is 4, which is greater than 0. Next question. Under what conditions does inequality hold? Delta S is enthalpy over temperature. In general, entropy is calculated by integration of reversible heat over temperature. This equation can be simplified by just Q over T if temperature is constant and reversible. So, as long as temperature is constant, you can use this equation, just Q over T. The Q can be replaced by enthalpy change under constant pressure, because constant pressure process, Q is enthalpy change, heat is enthalpy change. And therefore, this inequality holds if the process is reversible, isothermal, and constant pressure. One example is phase transition. For phase transition, it is a constant temperature, constant pressure, reversible, and the delta S for phase transition is the phase transition enthalpy over phase transition temperature. In this question, it asks you to calculate QW, delta U, delta H, delta S for a reversible isothermal expansion. From last chapter, you learned that for isothermal expansion, delta U, delta H are both zeros, and the work is negative nRT ln V2 over V1. Now the question tells you the pressure is half of initial volume. So Boyle's law tells us P1 V1 equals P2 V2. So V2 over V1 should equals to P1 over P2. Okay, and because question tells you the pressure, final pressure is half initial pressure, so this equals P1 divided by half P1, and that gives you 2. And so the work should be negative nRT ln 2. Okay, that's why you have ln 2. All right. And according to the first law, delta U equals Q plus W, and so the Q should equal to negative W. Now the only thing new in this chapter is how to calculate entropy. So the entropy is calculated for constant temperature to be Q divided by T. As long as it's constant temperature, is Q divided by T if it's reversible. Alright, so the Q is calculated here, divided by T, you can calculate delta S in this way. In the class, we also derived equation for ideal gas isothermal expansion, and the equation is nR ln V2 over V1. Okay, note the difference, this equation and this equation. Okay, this is for work. And note that in the equation for work, you have a temperature. And here, for entropy, you don't. The reason is this equation. Entropy is Q divided by T, and Q is negative W, so negative sign is cancelled. And then divide by temperature, so temperature is also cancelled. And then you get nR ln V2 over. That's the entropy for isothermal reversible expansion. So you have two methods to calculate entropy change in this question. Alright, both give you the same answer. Next, ask you to calculate the surrounding entropy. Surrounding entropy is calculated by the Q surrounding divided by T surrounding. If you don't know Q surrounding, you use negative Q system. So it's negative Q of the system. Here is the system. Okay, and the total entropy, you add these two together, give you 0, which is not surprising because it's reversible. Okay, it's reversible. And the second law says, for reversible process, the total entropy should not change. Delta S 0. Alright, if it's spontaneous, delta S is greater than 0. So combine these two together, delta S is greater or equal to 0. Remember, that's the second law for entropy change. This is the total entropy. And because it's reversible, so there's no natural direction of change in the process. Calculate entropy change if temperature of 1 mole ideal gas with constant volume heat capacity 3/2R is increased from 150 to 350 Kelvin under A. constant volume, B. constant pressure. So this question is about entropy change when temperature change. So in class, we derived the two equations. One is for constant volume, one is for constant pressure. So for constant volume, the entropy change is NCVM ln T2 over T1. And for constant pressure, is NCPM ln T2 over T1. Okay, the calculated entropy, one is 10.6, the other is 17.66. The question is, are these processes spontaneous? Because they both are positive, so it seems that the entropy increase suggests that the process is spontaneous. But again, you must remember the second law says the entropy must increase for the whole universe, not just the system or surrounding. So here we calculate entropy increase for the system, but we do need the surrounding. If we don't have the surrounding entropy change, we cannot predict whether the process is spontaneous or non-spontaneous. And therefore, the answer is we don't know. We need more information to answer this question.